The University of Rio Grande Valley's Micro-G NExT team designed and tested their handcrafted regolith auger at NASA's Johnson Space Center. The prototype is manually operated and was tested underwater at the Neutral Buoyancy Lab. The team's coring device was designed to be used by astronauts taking samples from asteroids. Before submerging to the underwater demonstration platform, a team of divers was instructed how to use the auger. Immediately following, the device demonstration was carried out with the university team providing real-time instructions to the divers through a one-way communication system from the control room. The regolith auger proved successful and was the culmination of intense research, meticulous design, and a deep commitment to the project by UTRGV students Varda Ahmed, Tuba Safir, and Christopher Curry. They share their story.
NASA hosts this competition called Micro-G NExT, where they invite undergraduate engineers, mathematicians, STEM students to build and address a current existing space exploration problem. This year, the year that we competed, they announced 5 projects, and we were to select one. Do you remember what it was called? It's called asteroid coring device.
No.
Is it coring challenge? I don't think it was called regolith.
Oh, coring device for regolith. That's what it was called. Yeah.
Unsexy name.
Yeah. So that was a challenge.
Yeah, it was a challenge.
We decided to address the regolith coring challenge because as soon as a team, when we read the challenges, that one immediately popped up.
We were just thinking about sample collection, so we were like, well, if, when you do ice coring, how did they collect that sample? We were thinking about melting and like, I guess like drill bits at the end of the cores, how they cut through the ice. So we're like, well, that's very relevant to this design, to this challenge.
And another reason we chose this, or at least my reason for choosing this project, is this is kind of the end goal of NASA's end goal. They want to find an asteroid, to have a device to attach onto it, kind of a harpoon-like, to tether it. Because asteroids are so small, if you tried landing anything on it, it would push it away because of gravity. So they land on it, then they would send an astronaut on a tether to this hook line, hook him onto it. He would use a tether himself to the asteroid, and then take the drill a core sample, and then return that core sample to his ship, and then back to
which is why we have tether attachment points, so that the astronaut...
Yeah, they would be carrying his on his belt, as well as the sample containment too. So he could go, take a sample, pull it out, take another sample.
Nothing will float away from his persons as he's working.
And that's why we have it on all the...
On every single component.
Right. We started with hand-drawn sketches. That was what we submitted to the proposal. And then after that, we used AutoCAD to implement our drawings.
We all worked on different parts of it. We did have an independent company that works with a lot of students through here, and we had them do some of the more difficult parts, because this was one 5-foot-long solid chunk of aluminum. So this had to be carved out completely.
This was like one separate piece, and we had to...
Yeah, we had sheets of aluminum as well.
Mm-hmm.
So this was carved out of the sheet, and then they pulled it so it kind of got into the long conical shape, and then they soldered it on, or welded it on.
They welded it on, and then we took it to another company, and they did all the welding. We were taking turns going to the machine shop and standing there, making sure that they are doing exactly what we wanted. There were definitely a lot of changes made right then and there.
Our initial idea was to 3D print our device. We weren't able to do that because the steel printer broke down, so we had to cancel our order, and that same day decide that maybe we'll just carve it out of the solid rod of aluminum, and then we ordered that on the same day.
What's the solid rod?
It was about $500.
How'd you guys get the money?
Funding from UTRGV.
This ended up being the best option for us, but it was also the most time-consuming.
The biggest challenge that we overcame, only because of the quality of advisors and faculty that we had help us, was the funding issue. Without our wonderful Dr. Brea, we would have no clue who to go to, who to ask to start the process of getting funding for these for our project parts.
got the approval that they were going to the finals. That was now give us support for printing and metal finishing and engineering. When hiccups came up through that, we had to go to Plan B and C, and that one I was there for Plan B and C. So she has been a key in supporting us throughout the project. So thank you.
Oh, you're so welcome.
This is the outermost compartment, and starting from below, you can see we have spirals that are welded on the conical part of the outermost compartment. And what that is going to do is when you're drilling, it removes the material and pushes it upward and displaces it outward. So that helps us with the drilling concept. And then we have the middle compartment. You can see it's this area. And that helps with the alignment and disalignment of the drainage holes. So when they're aligned, water will pass through. And when they're not aligned, sand cannot go inside the prototype when you're drilling. And then we have, this is what's called the innermost compartment. This is where the sample is collected. And this sits right between this cylindrical component, and that's just there to keep it from wobbling. So once you place it inside, this tether attachment would not be there. This is only there for after the sample has been collected and removed from the prototype. But for this case, I'm just gonna leave it on. And what you would do is add this. So you screw it on top of the outermost compartment. And there's a little protrusion right here. And that applies pressure to the innermost compartment and keeps it from wobbling back and forth. That way your sample can collect with the layers intact, so you don't have disrupted layers. And so this is how your prototype would look while you are drilling.
Oh yeah. And the integration. So you did some software there.
Oh yes, definitely.
Yeah.
In fact, we consulted with several engineering faculty. They were very impressed. They considered this to be a senior project. They thought it was a sophomore at the time. So I'm very proud of these kids. They really leaped forward at the challenge.
It started out within a few months. It started out with just an abstract form in our head. And within a few months, and with our own manual labor and with our own blood and sweat, we were able to make a physical device that works, that's gonna last us forever. I mean, it was really confidence-boosting, especially as an engineer, to know that we could take it from step one all the way to the end by ourselves, with everyone's help, obviously. But yeah, we were able to do it ourselves. We just put in our own work.